In this session, we will discuss forced oscillations and resonance. Forced oscillators are also known as driven oscillators. Driven harmonic oscillators are damped oscillators further affected by an externally applied periodic force. If the forcing frequency is close to the natural frequency of the system and the system is lightly damped, huge vibration amplitudes may occur. This phenomenon is known as resonance. As a general rule, engineers try to avoid resonance like the novel coronavirus. Resonance can be bad vibrations. Large amplitude vibrations imply large forces, and large forces cause material failure. There are exceptions to this rule, of course. Musical instruments, for example, are supposed to resonate so as to amplify sound. Musicians who play string, wind instruments spend years training their lips or bowing arm to excite just the right vibration modes in their instruments to make them sound perfect. Resonance is a good thing in energy harvesting systems, and many instruments such as MEMS gyroscopes and atomic force microscopes work by measuring how external stimulus of some sort like a rotation or a surface force changes the resonant frequency of a system. Forced harmonic oscillator. Let us consider a damped harmonic oscillator which is being acted upon by an external periodic force. So the forces on the damped system are the restoring force as well as the damping force. The damping force given by negative BV and the restoring force given by negative Kx. Let the external periodic force be F0 sine omega Ft, where omega F represents the angular frequency of the external periodic force. So we have different terms, omega naught being in the natural angular frequency, omega the damping frequency, a damped angular frequency which is root of omega naught square minus beta square, and here omega F is the angular frequency of the external forced oscillator, and the frequency of the forced oscillator will be given by dividing omega naught with 2 pi. So the net force on the system will be sum of all these forces, that is the damping force, the elastic restoring force, and the external periodic force. Now the net force can be written as ME, as in the case of the same damped harmonic oscillator system, so that the total force will be ME is equal to negative BV negative Kx plus F0 sine omega Ft. Taking the damping force and the restoring force to the LHS and writing in the differential form, we have acceleration d square x by dt square and velocity as dx by dt. Since b by m is 2 beta and k by m is omega naught square, we will be replacing f0 with small f0 by m, so that on dividing the previous equation throughout by m, we have d square x by dt square plus 2 beta dx by dt plus omega naught square is equal to small f0 sine omega ft. The small f0 is capital F0 divided by m, as said earlier. Now this represents the differential equation of a forced harmonic oscillator. This equation is a non-homogeneous differential equation of second order. Now let us find the solution of the differential equation of a forced harmonic oscillator. So d square x by dt square plus 2 beta dx by dt plus omega naught square is equal to 0 is the differential equation of a damped harmonic oscillator, and that equal to small f0 sine omega ft is the differential equation of a forced harmonic oscillator, which is equation 1. Now the solution should contain two parts, as it is a non-homogeneous second order differential equation. The first part will be a complementary function where the LHS should be equal to 0, and being oscillatory, that will be the same solution as that of the underdamped case in the damped harmonic oscillator, which is x is equal to a naught e raised to minus beta t sine omega f t. The second part will be the particular integral part, which we will be finding it by the trial and error method. So we will find the particular integral part and combine the solution to get a complete solution. So let us take the solution of equation 1 as x is equal to a sine omega f t plus phi. We have chosen this solution because being a periodic driven force, the motion should be of course oscillator, so it should contain a periodic function. To find the particular integral part, let us assume the solution as to a sine omega f t minus theta. We have assumed this solution because the system is driven by a periodic force, so the motion should be periodic. So we have a periodic term, the sine function term. A is the amplitude, and theta is the phase difference which can account between the external periodic force and the displacement, if any. A is the amplitude, which we will be finding. So let us proceed the same usual method we have done in the differential equation for damped harmonic oscillator. So we will be taking the first and the second derivative dx by dt and d square x by dt square and substituting in equation 1, which is the differential equation of a forced harmonic oscillator. So the equation, we can write it as negative a omega f square sine omega f t minus theta, that is d square x by dt square, plus 2 beta times dx by dt, which is a omega f cos omega f t minus theta, and the next remaining term on LHS as a plus omega naught square x, where x is a sine omega f t minus theta. This is equal to f naught sine omega f t minus theta, where we will be having a slight rearrangement on the RHS part. Instead of sine omega f t, we will be writing it as sine omega f t minus theta plus theta, so that the value doesn't change. But we can do an adjustment here because the term on LHS contains both sine omega f t minus theta and cos omega f t minus theta. So we have f naught sine omega f t minus theta plus theta. So the value will be the same. We don't have any difference from the equation 1. So we have done is because this can be considered, omega f t minus theta can be considered as a single term, so that it will look like sine of a plus b, which can be expanded in the form sine a cos b plus cos a sine b. So expanding the RHS, f naught sine omega f t minus theta cos theta plus f naught cos omega f t minus theta sine theta. F naught is common, so we can take f naught common and write. We have done this because the LHS term after taking the first and second derivative consists of sine omega f t minus theta and cos omega f t minus theta. The equation looks bigger now, but we can easily simplify by taking the coefficients of cos omega f t minus theta and sine omega f t minus theta. So from LHS and RHS, let us take the coefficients of cos omega f t minus theta and sine omega f t minus theta and write. So the coefficient of cos omega f t minus theta, it has a single term here, 2 beta a omega f is equal to f naught sine theta, and the coefficient of sine omega f t minus theta in LHS have two terms. We have taken a common, so that a omega naught square minus omega f square is f naught cos theta. Those are equation 2 and equation 3. Yes, we have f naught sine theta and f naught cos theta, and you can easily get rid of those sin theta and cos theta as sin square theta plus cos square theta is equal to 1. That's why we can square and add equation 2 and 3, 4 beta square a omega f square plus a square omega naught square minus omega f square the whole square is equal to f naught square. Taking a square common in LHS and taking the other terms to the RHS and taking the square root, we will get the amplitude as f naught divided by root of 4 beta square omega f square plus omega naught square minus omega f square the whole square, which is equation 4. This is the amplitude of the forced harmonic oscillator. So we will substitute this in the assumed solution, which is x is equal to a sin omega f t minus theta. So we had said that theta is the phase difference between the applied force and the displacement, if any. The value of theta can easily be found out by taking the ratio of equation 2 and equation 3, that sin theta by cos theta is tan theta. So the particular integral part will be replacing a in the assumed solution as equation 4. We have f naught sin omega f t minus theta divided by a root of 4 beta square omega f square omega naught square minus omega f square the whole square. Now from 2 and 3, tan theta will be given by 2 beta omega f divided by omega naught square minus omega f square, as the a term cancels. So theta in the particular integral part is obtained from theta is equal to tan inverse 2 beta omega f divided by omega naught square minus omega f square. So this leads to our solution to the differential equation of a forced harmonic oscillator. The differential equation for the forced harmonic oscillator, that is represented by equation 1, d square x by dt square plus 2 beta dx by dt plus omega naught square x is equal to f naught sin omega f t, sum of two parts, complementary function and particular integral. The complementary function is a naught e raised to negative beta t sin omega t plus phi, which is the solution to the underdamped condition, that is LHS of equation 1 equal to 0, and we obtain the particular integral part as f naught divided by root of 4 beta square omega square plus omega naught square minus omega f square the whole square times sin omega f t minus theta. Now this is a complete solution, but with the passage of time the external periodic force takes over, so that the first term, that is a complementary function, vanishes with time, so that the final solution will be the particular integral part only, that is x is equal to f naught divided by root of 4 beta square omega f square plus omega naught square minus omega f square the whole square. So this is the final solution for differential equation of forced harmonic oscillator. From the previous equation, we have seen that the amplitude of a forced harmonic oscillator depends upon beta and omega f, that is the damping coefficient and the frequency of the external forced oscillation. Omega naught is a natural frequency which is a constant, so amplitude can vary depending upon these factors. So let us analyze the condition for that the amplitude is maximum. For the amplitude to be maximum, the denominator of the term should be minimum. Or we can rather say here in this situation that d by d omega f of omega naught square minus omega f square the whole square plus 4 beta square omega f square should be equal to 0. Now differentiating with respect to omega f and simplifying, taking the common terms, we will get omega f is equal to root of omega naught square minus 2 beta square. So this is the condition of the external frequency at which the amplitude becomes maximum. That is the resonant frequency. So correspondingly, omega r is equal to root of omega naught square minus 2 beta square is the angular resonant frequency. If beta is 0, the angular resonant frequency is same as the natural angular frequency, which is the ideal condition of simple harmonic motion. In order to find the maximum amplitude, we will substitute the value of the angular resonant frequency instead of omega f in the equation for amplitude. And by simplifying, we have A maximum, that is the maximum amplitude, is equal to f naught divided by 2 beta omega, as omega is root of omega naught square minus beta square. This can be written as f naught tau by omega, where tau is the relaxation time, which is numerically equal to 1 by 2 beta. This is the time taken by the initial amplitude to decrease to 1 by e of the initial value. We can plot a graph between the amplitude and the external forced frequency so that we can find the frequency, that is the resonant frequency at which the amplitude is maximum. So on increasing beta, the resonant frequency is found to be decreasing from the natural frequency, and also the amplitude decreases. It is interesting to note that the width of the resonance curves shown in the figure depends on damping. The less the damping, the narrower the resonance. The message is that if you want a driven oscillator to resonate at a very specific frequency, you need as little damping as possible. Little damping is a case for piano strings and many other musical instruments. Conversely, if you want small amplitude oscillations, such as in a car suspension system, then you want heavy damping. Heavy damping reduces the amplitude, but the trade-off is that the system responds at more frequencies. These features of driven harmonic oscillators apply to a huge variety of systems. When you tune a radio, for example, you are adjusting its resonant frequency so that it only oscillates to the desired station's broadcast, that is the driving frequency. The more selective the radio is in discriminating between the stations, the smaller its damping. Magnetic resonance imaging (MRI) is widely used medical diagnostic tool in which atomic nuclei, mostly hydrogen nuclei, are made to resonate by the incoming radio waves of the order of 1000 MHz. A child on a swing is driven by a parent at the swing's natural frequency to achieve maximum amplitude. In all of these cases, the efficiency of energy transfer from the driving force into the oscillator is best at resonance. Next is the analogy between electrical oscillator and a forced mechanical oscillator. We have the series LCR circuit driven by an alternating voltage compared to the forced mechanical oscillator. So let us initially discuss what is an LC oscillation. A fully charged capacitor, when discharged through an inductor, the charge oscillates between the two plates through the inductor. This is known as LC oscillation. An inductor is a device consisting of a coil. A capacitor is a device containing two parallel plates. Now the charged capacitor is allowed to discharge through the inductor, and current flows between the two plates of the capacitor through the inductor. The frequency is known as the resonant frequency in ideal condition. That is, under ideal condition, the circuit will have current forever. Now let us consider an inductor of self-inductance L, capacitor of capacitance C, and a resistance of resistor R connected in series, applied with an alternating voltage V equal to V0 sin omega ft. There will be a potential difference across each component as the capacitor gets charged and discharged repeatedly by the external voltage. So we can apply the Kirchhoff's second law, that is a voltage law or loop rule in the circuit. The potential difference across the inductor is L di by dt, and that across the resistor is I times R, and that across the capacitor is Q by C. So the algebraic sum of EMF and potential difference across the loop is written. The current I is a time rate of flow of electric charge, can be written as dq by dt, and we will write di by dt as a d square q by dt square. So the equation is modified as L d square q by dt square plus R di by dt plus q by c is equal to V naught sin omega ft. Now we will divide the equation throughout with L and find that this is similar to the differential equation of a forced harmonic oscillator. By comparing with the standard equation, d square x by dt square plus b by m dx by dt, of course b by m is 2 beta, plus omega naught square x is equal to f naught sin omega ft. We have an analogy between the terms. R by L and B by M are equivalent. Wherever x is there, we have Q. So the electric charge is equivalent to the displacement. So resistance is equivalent to the damping constant. Self-inductance of the coil is equivalent to the mass, which is a factor of inertia. So the analogous terms can be written. So we have an analogy between an electrical oscillator and a mechanical forced oscillator in a series LCR circuit, which is driven by an alternating voltage. By comparing, the omega naught square is 1 by Lc, so omega naught is 1 by root Lc. That's why we have the natural frequency of an LC oscillating circuit is 1 by 2 pi root Lc, as frequency is omega naught divided by 2 pi. The equivalent of velocity is electric current, as equivalent of charge is displacement. So dx by dt is same as dq by dt.